Good morning, dear student. In previous lecture, we already discussed the C13 NMR spectra for organometallic compound, or we can say that the C13 chemical shift values for organometallic compound. In today's lecture, we are very much interested in the H1 NMR spectra, or we can consider the H1 chemical shift values for organometallic compound. So similar to C13 NMR spectroscopy, the H1 NMR spectroscopy, it is also useful to study the organometallic compound containing the hydrogens, and it will give the useful structural information. So what information we get from this H1 NMR spectra? Let us discuss one by one point. That is what information. So we get from this H1 NMR spectroscopy. The first important point is that this H1 NMR spectra or spectroscopy, H1 spectra of organometallic compounds containing containing hydrogen containing hydrogen can also provide useful structural information useful structural information. So what information is obtained from this H1 NMR spectroscopy? For example, if you consider the first one, that is most proton. The first point, if you consider most proton bonded directly to the metal atom, bonded directly to the metal. So whenever the proton it is directly bonded to the metal, then this complex is considered as a hydride complexes. So we are considering as a hydride complexes in which the proton having the negative charge. So the most proton bonded directly to the metal atom in hydride complexes are very strongly shielded, are very strongly shielded. So you are very much familiar with this shielding and de-shielding. Okay, so we already discussed the shielding and de-shielding in organic chemistry for studying the organic compound. So if you consider the first, what information we get from this H1 NMR spectroscopy, that most of the proton is bonded directly to the metal atom in the hydride complexes, are very much are strongly shielded, and with the chemical shift value. So as shielding is increases, the chemical shift value is decreases. So with chemical shift value, if you consider for the proton which is directly attached to the metal atom, with chemical shift value in the range of in the range of -5 to -20 ppm. So you should keep in mind the range for the proton which is directly bonded to the metal atom, that is -5 to -20 ppm. So this information we get from this H1 NMR spectroscopy, that is whenever the proton it is directly attached to the metal atom, then its value, that is its chemical shift value, is ranges from -5 to -20 ppm relative to the TMS, relative to TMS, that is tetramethyl silane, which is used as a reference in your H1 NMR spectroscopy, relative to the TMS, that is tetramethyl silane. So this is the first point. Again, if you consider The second important point regarding to this H1 NMR spectroscopy, that the proton, okay, so we already discussed the proton which is directly attached to the metal atom. If the methyl group is attached to the metal atom, so for this proton, that is the proton, uh, methylene proton, or what is the value of this methylene proton? So if you consider the proton in methyl complex, the proton in methyl complex, okay, when methyl group it is attached to the metal atom, methyl group is attached to the metal atom, so the proton in methyl complex typically typically have chemical shift, have chemical shift have chemical shift between 1 to 4 ppm, between 1 to 4 ppm. So whenever we considering the proton which is directly attached to the metal atom, then its delta value is -5 to -20 ppm. When we considering the methyl proton, which is methyl proton or methyl group, it is directly attached to the metal atom, its chemical shift value in this H1 NMR spectroscopy is 1 to 4 ppm. Again, if you consider the pi ligands cyclic pi ligands such as eta 5 C5H5, eta 5 C5H5, and eta 6 C6H6, C6H6, they having most, or they lie, okay, the chemical shift value is lie between 4 to 7 ppm, 4 to 7 ppm. So these are the some important ligands, okay. So whenever the proton is directly bonded, its value is -5 to -20 ppm. Then the methylene proton having the value of 1 to 4 ppm. Whenever we consider the cyclic pi ligand such as eta 5 C5H5 and eta C6H6, its value is lie between 4 to 7 ppm. Okay, so these are the some common ligands and their chemical shift value. So let us discuss some ligands which is attached, or the proton which is attached. We can considering the chemical shift values for organometallic complexes in which the proton which is directly attached to the metal atom, or it is methylenic proton, or it is the carbon-carbon double bond proton, or the protons of ferrocene. So let's discuss these values. So yeah, similar to C13, we discussing the H1 values for different complexes. So the chemical shift for organometallic compounds, so specific compound is given and its chemical shift value is given. So you just understand that is the complex. At one side the complex is given, and another side the H1 chemical shift value is given. H1 chemical shift value is given. H1 chemical shift value is given. If you consider the first one, that is MnCO by 5 and MnCO by 5 and H. So in this case, there is a total 5 carbonyl ligand and one proton. It is directly attached to this, one proton which is directly attached to this metal atom. So its value is given, that is -7.5 ppm. So when the metal atom is Mn, so this is Mn complex. Second, that is WCH3 by 6, that is the tungsten metal is there, and all this methyl proton is there. Okay, so all this methyl group, 6 methyl group is there, and if you consider its H1 chemical shift value, it is 1.80 ppm. So we are considering this proton, that is methylene proton, this proton. So this is the value. Okay, the next one, that is your if you consider the next complex, that is your nickel complex, in which the hepticity of this ligand is 2, that is your ethylene ligand C2H4 thrice, C2H4 thrice. And we are discussing the chemical shift value for this proton, that is ethylenic proton. Then it is up to 3.06 ppm, 3.06 ppm. So whenever the value is given in negative, if the ppm value is negative, it indicate the proton is directly bonded to the metal atom. When the value, if you consider this value 1.80, then it indicate it is a methyl proton. When the value is 3.06, it indicate the proton is your ethylene proton is there. So carbon carbon double bond, it is attached to the metal atom, it is your ethylene proton, and therefore its value is 3.06. Again, if you consider the next one, that is your ferrocene complex is there, that is eta 5 C5H5 twice, and this is your Fe. And for this proton, okay, the proton which is attached to this cyclopentadienyl ring in ferrocene, its value is 4.04 ppm, 4.04 ppm. So the value for this ferrocene, that is eta 5 C5H5, it's like it appear, or its delta value or chemical shift value is 4.04 ppm. Again, if you consider the next one, that is eta 6 C6H6 twice, eta 6H6 twice, it is your chromium complex. And for this proton, that is for this hydrogen atom, its value is 4.12 ppm. So we already discussed for cyclic pi ligands such as eta 5 Cp and eta 6 C6H6, the values lie between 4 to 7 ppm. So this is the characteristics value. One more is there. If you consider one more is there, that is this complex, that is eta 5 C5H5 twice. So this value for this proton, okay, underlying proton is there. So eta 5 C5H5 twice, then tantalum is there, okay, metal atom is tantalum, then one of the methyl group is there, and again it is attached to carbon carbon double bond. That is when it is attached to the carbene, we can consider, that is CS2. This carbon, it is attached to this metal atom. So okay, there is a double bond between this carbon and metal atom. And for this proton, so we are considering this carbon carbon double bonded proton. So this value is, we know that is whenever it is attached to methyl, then its value is 1 to 4 ppm. So we already discussed that whenever the methyl proton is there, it is 1 to 4 ppm. Whenever the ferrocene is there, or cyclopentadienyl proton is there, then it is from 4 to 7 ppm. So for this vinyl proton, so we are considering here the carbon carbon double bonded proton, its value is 10.22 ppm, 10.22 ppm. So these are the some important values, okay, H1 chemical shift values for different organometallic compound. So we are discussing, whenever we solve the numericals on this given data, we can easily identify the structure of the compound with the help of this H1 chemical shift value and C13 chemical shift value. So this is all about the chemical shift value for this organometallic complex, that is H1 chemical shift value for this organometallic complex. At least you should keep in mind these 2 3 4 values for solving the numericals. Again, if you consider these complexes, that is whenever if you consider this pi ligands, okay, cyclic pi ligand, they shows fluxonial behavior, okay. So this fluxonial behavior, what is this fluxonial behavior? So you should keep in mind whenever the ligand, okay, like this, what is the fluxonial behavior? So you should keep in mind. So this is your ligand, this is your eta 3 C3H5, its hepticity is 5, and if you consider it is attached to the metal atom, and if you consider it having a two sets of proton, not two sets of protons, so we're discussing the proton, so it having total three carbons, its hepticity is 3, so it is considered as eta 3 C3H5. And if you consider these protons, okay, so at low temperature it will shows 3 signal in H1 NMR spectroscopy. So this is if you consider this proton, so this is your A type of proton, this is your B type of proton, and this is your C type of proton. So at low temperature we get 3 NMR signal, 3 H1 NMR signal for these ligands, that is eta 3 C3H5 ligands. But at low temperature means at negative temperature, so you should keep in mind that is at negative temperature. Negative temperature is considered as a low temperature. Okay, so different types of proton is there. Okay, so at low temperature we get 3 H1 NMR signal, okay, or 3 kinds of proton is there. Okay, but at high temperature we get only two signal in H1 NMR, two signal in H1 NMR, because at high temperature, so at high temperature means at room temperature, this eta 3 C3H5 ligand shows fluxonial behavior. It will shows fluxonial behavior. So this proton, that is A type of protons and this B type of proton, so this AB type of proton, in this case this AB type of proton, they are exchange, so the exchange is very rapid that NMR instrument cannot detect this exchange, and therefore for this proton, for this two proton, we get for this proton, that is AB proton, we get only one signal. So there is a rapid exchange of this AB proton, so this exchange is very rapid, so the NMR instrument cannot detect this exchange, and therefore for all these four protons, that is this AB and this AB proton, we get only one signal, and for this C type of proton we get one signal. So at high temperature we get only two signal, because there is an interconversion of this syn and antiproton. So with respect to this metal atom, two protons are syn and two protons are anti, so the syn and antiprotons are exchanged rapidly, okay, and the NMR instrument cannot detect this proton or cannot detect this exchange, okay. This exchange is very rapid and the NMR instrument cannot detect this proton, that is a rapid exchange of this proton, and therefore for all these four proton we get only one signal in NMR spectroscopy, H1 NMR spectroscopy, and another signal for this HC proton. So we get two signal in H1 NMR spectroscopy, and this behavior is called as a fluxonial behavior. So this is for eta 3 C3H5. If you consider the another one, that is your cyclopentadienyl ligand, in which if you consider the hepticity of this ligand is 1, it is attached to the metal atom, its hepticity is eta 1 C5H5, similarly as C3H5. So at low temperature, if you consider at low temperature, so in this case if you consider this is hydrogen, this is hydrogen, and this is hydrogen, okay. So this is your A type of proton, this is your B type of proton, this is your C type of proton. So at low temperature means at negative temperature, it will shows three signal. So why it will shows three signal? Because there is a three sets of proton, and at low temperature the molecule is a rigid one. It is rigid. Okay, so at low temperature means at negative temperature it will shows 3 signal in H1 NMR spectroscopy, and it is a rigid molecule. The molecule is rigid at low temperature. Okay, so the NMR instrument can detect 3 sets of proton. Okay, but at high temperature, when the molecule is non-rigid, at high temperature the molecule is non-rigid, and at high temperature means at room temperature. So you should keep in mind, at high temperature means the molecule is in non-rigid state, and at room temperature, okay, high temperature is considered as a room temperature, it will shows the fluxonial behavior. And at high temperature we get only one NMR signal, only one H1 NMR signal for this cyclopentadienyl proton NMR signal. Okay, so at low temperature, that is at negative temperature, the molecule is rigid and we get 3 signal. Okay, 3 sets of protons. So in this case there is a 3 sets of protons, so we get 3 signal. But at high temperature the molecule shows the fluxonial behavior, so there is an exchange of this proton. So if you consider there is a sharp 1-2 exchange or 1-3 exchange. Okay, so the exchanges occur, okay, the intermediate in which there is a 1-2 exchange or 1-3 exchanges occur, and the exchange is very rapid that the NMR instrument cannot detect this exchange of this proton, and therefore at high temperature the molecule is non-rigid, means at room temperature we get only one H1 NMR signal. Again, if you consider for eta 3 C3, okay, this is for eta 1 C5H5, eta 1 C5H5. If you consider the second one, that is when the heptacity is 3, okay, when the heptacity is 3, so this is the case. So these 3 ligands, these 3 carbons are attached to the metal atom. Its heptacity is 3, that is eta 3 C5H5. So in this case also this molecule, this ligand, it shows fluxonial behavior. Again, at low temperature it is rigid and it will shows 3 signal. So there is a 3 sets of proton. Okay, it will shows 3 signal. Okay, so you keep in mind whenever we considering the eta 1 CP, then at low temperature it will shows, okay, it will shows 3 signal, and at high temperature it will shows only 1 signal due to the fluxonial behavior. If you consider this eta 3 C5H5, at low temperature it also shows 3 signals. So there is a 3 types of proton, okay, 3 sets of proton. So at low temperature it will shows 3 signal. Okay, at low temperature it will shows 3 signal. At low temperature means at minus degree temperature it will shows 3 signal, but at high temperature it will shows only 2 signal. But at high temperature it will shows only 2 signals. That this is your C, not B, this is your C. So there is also a rapid exchange of this B and C type of proton. So the NMR instrument cannot detect this interconversion, and therefore for this there is a rapid conversion of this B and C proton. We get only one peak, and for this A type of proton we get only one peak. So at high temperature we get only 2 signal. Okay, so we already discussed that at a high temperature we get only 2 signal. Okay, in this case for eta 1 we get 3 signal at low temperature and 1 signal at high temperature, because there is a 1-2 shift and 1-3 shift. Okay, so we cannot we cannot identify which proton is different one. So all these protons are equivalent proton, and therefore they gives only one signal. In this case At low temperature there is a 3 signal, but at high temperature there is a 2 signals, because this B and C type of protons, they are exchanged rapidly, so the NMR instrument cannot detect this proton, so we get only 2 signal, and such a behavior is called as fluxonial behavior. And if you consider the last one, that is your uh, when the hepticity is maximum, that is eta 5 C5 H5, eta 5 C5 H5. So you should keep in mind, at low temperature as well as at high temperature. So at low temperature means the molecule is resealed, at high temperature means the molecule is non resealed. Okay, at low temperature it will also shows one signal for all these equivalent proton, all these 5 protons. Okay, first, okay, these are the 5 proton is there, so it will shows one signal at low temperature, and it will shows one signal at high temperature. So all these protons are equivalent, means all these carbon atoms are attached to the metal atom, and the NMR instrument cannot NMR instrument gives only one signal, because all these protons are equivalent, so we cannot divide into different sets, that is, this is A type of proton, this is B type of proton, or this is C type of proton, because all the carbons are attached to the metal atom, and all these protons are equivalent proton, all these protons are equivalent proton. So at low temperature and at high temperature we get only one signal for this eta 5 CP, and this is called as a fluxonial behavior. So you should keep in mind 2 3 system, that is eta 1, eta 3, and eta 5. For eta 1 and for eta 1, at low temperature we get 3 peaks or 3 signal, at high temperature we get only one signal, only one signal. For eta 3 C5 H5, at low temperature we get 3 signal, and at high temperature we get only 2 signal. For eta 5 C5 H5, at low temperature we get only one signal, and at high temperature we get only one signal. So this is your fluxonial behavior, so you should keep in mind this fluxonial behavior. And in the next lecture we're discussing some numericals on this C13 chemical shift value and H1 chemical shift value. Thank you.